Two quick things before we get started. I'm going to make the lecture on one topic, perhaps finish more quickly than we did last time. And I'm going to leave one topic out for either another day or I'll just let it slide for now. Here's where we were last time. We're talking about dynamic programming algorithms. We talked about matrix chain multiplication, multiplying a bunch of matrices together, and you wanted to figure out the best way to associate them, in what order, which parentheses to do first to make the minimum number of multiplications when we were all done. And we had that little chart, and we had to go through the chart, and then we analyzed it really quickly at the end, and we figured out that it was, at least you took my word for it, order n cubed. And I talked a little bit about other dynamic programming things that relate to it. So before I go on, I want to do just a really quick math thing. And if you don't like this stuff from discrete math, then just turn your brain off for the next 5 minutes. The rest of you, I have a captive audience, and I can do this. I'll wake you up. Here's what we did last time. We had this chart that looked like this, and the ones down here, these took the least amount of time, right? Then the ones here, whoops. So let's say these took 1 step each. These took 2 steps each. These took 3 steps each. These took 4 steps each. And this one took 5 steps. Something like that, right? Because the most complicated one depended on all of them, the ones that were one diagonal depending on all the ones below that. And we tried to add this up. And we came up with the following kind of a formula. Basically, there's only one of these, and it takes 5 steps. There's 2 of these, it takes 4 steps. So we're basically starting with 5, going down to 1, but the number of time it takes for each level, this level takes 1 step, this one takes 2 steps, this one takes 3 steps, this takes 4. Did we do this right? I said exactly backwards. I'm fine. This takes. So there's one of these, it takes 5 steps. 2 of these, they take 4 steps. So the numbers reverse. So we get a sum that looks like this. 1 times n plus 2 times n minus 1 plus 3 times n minus 2 all the way up to n times 1. It just reverses. And we wondered, how big this was. So let's do a quick calculation. Let's say everything was kind of like this n. If everything was like this n, then we're adding up n n's, and it'd be like n squared. Right? That's the lowest it's going to be. And the middle one is going to be about what? It's going to be about n over 2 times half and half. The middle guy. Somewhere in the middle here, there's going to be something that looks like this. And that's about n squared. So if it was like that one the whole way through, the whole thing would be n cubed. There'd be n squareds. So what is it? Is it really n squared or is it n cubed? And the reason I'm doing this, and I'll take 5 minutes to do it, is because I want you to see that sometimes the constant factors aren't always big. Sometimes they're 180, sometimes they're 4, sometimes they're 2. So in this example, the constant factor is 1/6. So even though this is an order n cubed algorithm, the constant factor and the engineering issues make it relatively quick. So let's see why. Let's see why when we add this up, we get something on the order of 1/6 n cubed. So here's what the sum looks like. Let's write this a little more mathematician-like. We're going to add up a whole bunch of things. And k is going to be an index that goes from 1 to n, 1, 2, 3 up to n. And what's the other side going to be? N minus k plus 1. Now that I've said that, in this situation here, I'll just leave it. The truth is that we can get rid of the 1 and make it a little easier. But I'll leave the 1 in there. Let's just do it. How do you sum up something like this? Well, you do it in pieces, and you just go back and look up what you did in discrete math and figure out what it equals. So here's what you get. You get a sum from 1 to n of kn, and a sum from 1 to n of k squared, and then you add on a sum from 1 to n of k. Just break it into pieces. Okay? And each one of these pieces is something that you can do pretty quickly. The n here, k is the thing that's ranging, so the n here doesn't change. You can factor it on the outside. So this is n times the sum of the numbers 1 through n, which is n times n plus 1 over 2. Okay, you pull the n out and add up the numbers to k. You get n times n plus 1 over 2. Those are the triangle numbers. Then we're going to subtract the sum of all the squares. We spent the day going through the sum of all the squares, and it ends up being this. And then you add in another sum of the numbers. And to make a long story short, because it's just a bunch of algebra, if you add it all up and fiddle with it, when you're done, you get something like n cubed over 6. Okay? So that's how you sum things like this. And you should know about this because the same summation comes up in the example we're going to do later today. Okay, in the parsing example. And it's going to be an example of a problem that you really have never seen in any of the classes in this curriculum before. So that's why I want to kind of spend some time introducing the problem and then some time working through the dynamic programming part of it, which will be kind of similar in style to what you did here with this diagram and this analysis. So we won't have to go through this analysis again later, and we can concentrate on the application itself as well as the meaning of how it connects to dynamic programming. Okay, questions about this little extra thing? Yeah, Teresa.
Definition of parsing is it?
Yeah, we're going to. I will. Not right this second. Oh yeah. So you want to think of it's looking at a potential program and deciding whether it's syntactically right. Looking for things like missing semicolons, mismatched parentheses, wrong kinds of identifiers, starting with a digit instead of a letter, an if statement that doesn't have the brace in the right spot, a while statement that doesn't have the word do following it, structures that are supposed to be hierarchical that don't, because you have the brace that closed up something and then you open something new before you finish closing the old brace, things like that.
Instead of software coming in, somebody's written to do all this.
I'll go with a yes on that. I'm going to get back to it in 2 minutes.
Okay, thank you.
All right, next thing. This is just a fun thing. I mentioned yesterday, and Mark printed out the paper for me, so it's kind of neat. This is a paper by Kozin and Zaks. Zaks is from Israel at the Technion, and Kozin is from Cornell. And they wrote a really cool paper about how you know, given a bunch of coins, whether you can do the greedy approach or whether you can do the dynamic programming approach. So in this paper, it's right here. It's a cool paper. This paper has a section that proves that this problem is NP complete. If I give you a bunch of coins and I ask you, does the dynamic programming approach work? The answer is always yes. But if I ask you, does the greedy approach work? The answer is sometimes yes and sometimes no, depending on what the denominations of the coins are. In the United States, 1, 5, 10, 25, 50, that denomination of coins, that works for the greedy approach. You can just do a greedy approach and get the smallest amount of coins per change. My 6-year-old can do that. But if that wasn't the denominations, it's possible the greedy approach doesn't work, and then only the dynamic programming approach works, and that's a lot more work and a lot more difficult for somebody to just do at first sight. So you'd like to know, given a set of coins, whether one works or the other works. So the problem is in general NP complete. But they give an algorithm to solve it anyway. The algorithm, by its own nature of the problem being NP complete, is going to be a slow algorithm, but it's elegant in its own way. And I want you to see the algorithm and still appreciate the fact that it's NP complete in the worst case, but you'll be able to understand it because the algorithm's based, the hard part of this paper and all the math is at the heart of why the algorithm works, and I can just tell you that result and compartmentalize all the hard stuff. So here's what their result says. Their result says, say you're given a whole bunch of coin denominations. Say 1, 3, 7, 8, 15, and 24. Okay, you're on, who knows, Pluto land, and that's what the coins are. And all the coins are of these denominations, 24-cent coins, 7-cent coins, etc. Then here's what they say. They say that if the greedy approach isn't going to work, if there's a flaw in using the greedy approach, then it's going to happen for particular values of change. And their theorem says exactly what range that change has to be in. And it knocks it down to a finite number of possibilities. And here's what they say. It has to be in between, strictly in between, something less than 15 and something bigger than, in other words, something less than the top two, and something bigger than the 1, 2, 3. Something bigger than this number plus 1. So something bigger than 8. So go to the third coin, add 1 to it. Go to the top two coins. And in between there, that's the range where the exception has to be.
It's the sum of the top two coins.
The sum of the top two coins. Oh, so it's, right. So it's 15, 24 gives you 39. And the third coin is 7. Add 1 to it gives you 8. So somewhere in this range, between 8 and 39, if the greedy problem is not going to work, you can find an example in this range where it won't work. This means all you have to do is try all these numbers using the dynamic programming approach, compare them to what you get with the greedy approach, and if there's ever a disagreement, it means the greedy approach doesn't work in general, and you don't have to try any of the other numbers all the way to infinity. That the example's got to be in this range. This is a really nice theorem because it lets you write an algorithm that determines which ones to try. And if the greedy approach doesn't work, you'll find it there.
Is this specifically for 6 coins, or
Any number of coins, you go to the second to last, you add the last and the second to last together, that gives you this bound, and you go to the third one and add 1, and that gives you the lower bound. So in between there, that's where it's going to happen. It's a nice result. So what do you do in this problem if you want to figure out if the greedy problem works or doesn't work? What do? You just try it on all the numbers between 9 and 38. And that's enough.
You have to compare it to something.
You have to compare it to see if it's the right answer. You can compare it to the dynamic programming algorithm. What's up, Erica?
Nothing. That's very strange.
Isn't it interesting? Yeah, surprising. Why is that NP-complete, this algorithm? I mean, not why is this algorithm NP-complete. The problem is NP-complete. So why is this algorithm, worst case, take a long time?
you could have any number of coins of any denomination? You could have a billion.
So say I have 100 coins. How long does this algorithm take if I have 100 coins? What does it depend on? What is the complexity of this algorithm?
The size of the
The size of this range.
Right.
So it's the size of the two largest coins, more or less. But it's very possible if I have 100 coins that the size of my largest coin could be 2 to the 100th. So this algorithm would take 2 to the n steps, where n is the number of coins I have. That's right. Therefore, this algorithm runs in time proportional to the largest coin I have. And the largest coin I have, for the most part, is going to be much, much larger than the number of coins I have. Right? So that's why the algorithm doesn't give you a polynomial time solution, but it's still a nice result nevertheless, even though the problem's hard. Yeah? Rob?
There's an exponential order of growth the more points that you have, the more permutations for each change in that there are to check as well.
That's true, but their theorem lets you avoid that. All you have to do in their theorem is check between the range 9 and 38. So it's true, there's lots of combinations, but their theorem shows that you don't have to do that brute force. Their theorem says the only thing that really makes this hard is that the size of the coins are big. So, in particular, this problem is not NP-complete for coins that are restricted size. If I have n coins and the biggest one is say, n squared, okay? If I have 100 coins and the biggest coin is just the square of 100, then this is not an exponential algorithm anymore. This is going to be a polynomial time algorithm because this number is going to be at most n squared.
Now, Isn't it just semantic calling it NP complete? Because couldn't you just say that the order is based on the size of the largest coin and call that n? I mean, why are we saying that n is the number of coins?
Rob had a good question. He said, isn't it just semantic calling this NP complete? Why don't we just call the input size the size of the largest coin and say that this algorithm is big theta of the maximum coin, which we'll call m? Everyone understand Rob's question? He says, you know, why don't we just say this is polynomial in the size of the largest coin instead of pretending that it's NP complete? So it's a really good question, and there's a good answer. When we think about coins, like say the coin 865, and when we think about the number of coins, how many bytes does it take us to store the number of coins? 1 byte for each coin, say. You know, so 3, 6, 7. But it doesn't take us 865 bytes to store this one number. Right? It takes us, let's say every digit takes a byte. Say we store it as ASCII values. It takes us 3 bytes. So the normal size of a number is not its magnitude. The normal amount of space it takes up in the computer isn't its magnitude. It's the number of digits in the number. So how fast is this algorithm in terms of the size of this input? Let's call the size of this q. That's the right variable to make a judgment on. When you make an algorithm time judgment, you base it on how long does it take me relative to the size of what I just put in. If I put in n things, how many steps does it take? If I put in a big number whose value is m, its size is only q. How big is q? Q is the logarithm of m. It's the number of digits in the number. So if I have an algorithm that runs in order m, that's exponential in the size of this number, in the size of the input. So we'd still think of it as being a bad algorithm. It's linear in something, but that something is not what we normally put in. This comes up in a much more important example. People always will tell you that factoring is hard. That's how you do RSA encryption. Right? Factoring is tough. It's not NP complete, but everybody thinks it's not going to be a polynomial time algorithm either. Nobody knows how to factor large numbers quickly. But you all know how to factor large numbers, right? How long would it take you to factor a number like this? How many steps, worst case? Chris says you can go up to the square root. That's true. That's to check if it's prime. But if you actually want to factor it, you're going to have to go through more steps afterwards. You'll have to do it again. Well, regardless, square root of n, n over 2, it looks like it's polynomial time, right? So what are people talking about when they say that factoring is hard? It's that the size of this input is not the number n. n equals 16851, but the size, the amount of space it takes in the computer is much smaller. It's only 5 bytes. So if I come up with a number, say, that's 100 bytes long, I'm not going to solve this factoring problem in time proportional to a polynomial in that 100. I'm going to solve it in time proportional to the actual number itself, which is like 2 to the 100th in size. So when we talk about factoring, it's a hard problem because the size of the number is much, much smaller than the number itself by an exponential factor. So there's no polynomial time algorithm proportional to the size of this that we know about. The one that Chris came up with is proportional to the exponential of the size, to the actual number itself. Does that make sense? So you asked a really good question. I took a long time to answer it because it's an important point. And when you discover that question, you should really try to grasp the answer. It's a little bit tricky, and there's a little semantics in it. So it's easy to kind of mess up. Is that completely okay?
Yeah.
All right. Any other questions? So get my eraser. Questions? All right. That's what I wanted to talk about to start with. Now let's start a different topic. Talk about parsing. All right. Here we go. Parsing is a very important topic, and I have to say that in all the wonderful things we do in the curriculum here in the 1 year that you're here, you don't get to have a course directly in compilers. So you don't get to spend a lot of time talking about what parsing is. Parsing is one of the fundamental legs of doing a compiler, of writing a compiler. You saw a little bit of it in Scheme with interpreters and meta-evaluators, and you'll see a little bit from the theoretical point of view in theory of computation. But you can have a whole course that just concentrates on compiler design, a big chunk of which talks about parsing. And there's been a lot of research just done on this one stage. So very briefly now, I'm going to give you a short introduction to how compilers, very short, how compilers work, what the three stages are of doing compilation, how one of them is parsing, and then we'll talk about what parsing means, do an example, how it connects to programming languages, and then strip all that away and reduce it to just a regular problem in an algorithm that we're going to solve. Okay so far? So here's the general way compilers work. A compiler looks at your Java program and scans through it, and the first thing it does is it finds all the groups of letters that are really bigger chunks. Like it sees an IF and makes that into an if. It sees the word class and makes that into the word class, instead of it just being a bunch of bytes like IF space CL. All right, and that's called looking for the tokens. Right, and that part, I don't know what you want to call it, what, lexical analysis or scanning? I'll call it scanning. That part is basically done using techniques that involve finite state machines. It turns out that the set of all tokens in any normal programming language can be described by finite state machine. So you describe the finite state machine, and then you write a program to implement the finite state machine, and you scan through your code, and you tokenize everything. And now you're ready to go for the next pass. Now you have your program looking like a collection of bigger clumps. And the next step is parsing. I'll do this one last because it's the one we're going to talk about today. Parsing basically, I'll get back into the details in a minute, but basically looks at the code and makes sure that it's really a Java program, or it's really a C program. And it does it just syntactically. You know, is the symbol that follows the if there? Does the semicolon come where it's supposed to come? Is there a bracket in the right place? Is there a right equivalent sign, you know, in this expression in the if statement? It just checks whether it meets the standards of the language syntactically. It does not check whether what you wrote made any sense. Okay, you can write a program that doesn't make any sense, but it's a legal program. And if you run it, it just goes into some stupid infinite loop. So the last step is translation, we'll call it. And this step basically takes the program after it's been parsed, where you know it's a correct program, and tries to convert it somehow into something we can run on an underlying machine. If you want to think of it just in the simplest way, it turns each of these things into machine language commands and then executes them. So it takes all your complicated semantic interpretation and turns it into something that can run. This is maybe the easiest part, and these two are tricky. It's in this part where you're going to do all sorts of optimization and make your thing run faster than some other compiler might run. This step is a little less engineering oriented and better well understood for many years already. This step involves the ability to look at a program and say, yes, it's okay or not okay, according to the rules of this language. So when Teresa said before, so there's like software things that check every step. So every language you come up with, like Java or C or Fortran or any language, has to have a set of rules that say, this is a legal program in this language. Now, how do you describe those rules? All right, so it doesn't look like a big text on, and everybody describes it in their own way. Well, if statements kind of look like this, and make sure there's a closed bracket and an open bracket, and an expression can go inside. And then if you want to do an expression, go to page 8 and see what an expression does. But it isn't too far away from that. It's kind of a formalized version of that. A program starts with this symbol. After that, you can have any kind of identifiers with commas in between. After that, you better have a closed parenthesis. After that, there better be a semicolon. After that, you can have any number of these choices. The first one is this type. The second one is this type. Those are built up out of these types. And you can follow your way through this big dictionary of explanation and figure out somehow if a given string fits those rules. But it's tricky. What are the rules? So, the rules that define a programming language are abstracted away into something which is usually talked about in a theory of computation course, but which has tremendous applications to compilers, in an abstraction called a context-free grammar. Every programming language you come up with will have a context-free grammar like we use language, to describe the rules, the ways of putting together words to make a legitimate program in that language. That's how you define a language. When somebody says, I made up a new language, they better tell you what the context-free grammar is. The second thing they have to tell you is the semantic meaning of what's going on. But that's the main thing they first do at the beginning, is setting up the syntax structure of the language. Okay, are there questions so far? Does it make sense? All right, we're going to talk about what a context-free grammar looks like in a second. There's one little example that I used in the notes for an old language called Pascal, which is barely used anymore. But it'll give you a sense of what a fragment of a context-free grammar looks like. And after I do this and motivate how context-free grammars connect to programming languages, we're going to strip away the connection to programming languages, move away from parsing, and talk just about a context-free grammar isolated from programming language, and talk about how to parse it. Parsing a context-free grammar means I give you a potential string that came from this grammar, and you tell me if it really came from there or am I lying. Did this really come from the grammar or is it not? Is the programming language I gave you, is the program I gave you really part of the programming language, or is it a syntactic error? So this defines the structure, and the question of parsing is a given string part of that structure or not? Here's an example of a context-free grammar. Now I'm writing the way I usually do. Let me start to talk now before I write the rest of the example down. This is the start symbol of the grammar. This means that if you want to generate strings or potential sequences of characters that abide by my grammar's rules, you have to start with this capital S, and then you can produce this sequence of symbols. The ones in small letters are ones that will end up in the string when I'm all done. Program will be there. The open paren will be there, the closed paren will be there, the semicolon, the word end will be there. There should be a period at the end, or maybe a semicolon at the end. That'll be there. The capital letters I and B will eventually disappear. They represent other things that have to be substituted for, or they represent things that will produce other things. These small letters are called terminal symbols, or the special characters are terminal symbols. They will actually end up in your program when you're finished. So a legitimate program in this language would start out with the word program, would continue with an open paren, would have some sort of a thing that's called an I. We don't know what that is yet. You'd have a closed paren after that. Then you'd have a semicolon, some kind of a thing that's called a B. You'd have another semicolon, and some kind of a word end that has to be there, and then another semicolon. These things need to disappear and turn into some real terminal symbols, symbols that don't go away. Right? So what's I? I stands for, in this language, you can have basically identifiers with commas in between them, like X, comma Y, comma Z, or input, comma output. Those are the kind of words that show up in this programming language. And B stands for the body of your program. There's lots of choices for B. It can start out with a definition of an array or an if statement or a while loop. B is a long, long, complicated thing. So this is a fragment of a language. We're just going to figure out the I part and leave the B part for the rest of the 80 or 90 productions in this language. So here's what the I part looks like. As I told you, the I represents any kind of identifier, any kind of variable name you want to give it. And you can have commas in between them, as many as you want. So what's an identifier? You can start an identifier with capital L, which stands for a letter. Here's L. A, B, C, D, E, F, G, up through Z. These vertical lines just mean that L can be any one of these things. Think of them as an OR. Instead of me writing down L goes to A, L goes to B, L goes to Z, one after the other, I just write them straight like that. So it can be a letter. And after a letter, it can be followed with a continuation, which I'll call J. Here's the continuation. You can have another letter followed by that continuation, or you can have a digit followed by that continuation. I'm saying this as I write it so you can see the meaning behind these funny symbols. An identifier is a letter that continues on. The continuation is either another letter with the same continuation, with another identifier that follows it, or with another one of these that follows it, or a digit with another one of these that follows it. So basically, you can start with a letter and you can continue with a letter or a digit. And then you can keep doing this and doing this. And a digit is just all the values 0 through 9. How do you ever get rid of a J? J turns to LJ. Let's look at this. J turns to LJ. LJ can turn into LLJ, right? Because the second J turned into an LJ. LLJ can turn into LLDJ. If I just keep using these productions, I always end up with a J at the end. I can turn the L into an A, this L into a C, this digit into a 3. So I can get AC3. But how do I get rid of that J? You want the J to be able to disappear. That means the empty string. J can disappear. It can turn into nothing. So here is a grammar which generates identifiers. Identifiers are things that start with letters and continue with either letters or digits, and then they can eventually disappear. But I told you that this is not just a single identifier, but it can also have lots of them with commas in between. So not only can I go to LJ, but it can also go to another identifier with a comma in between and a second identifier. So I can be substituted for 2 identifiers with commas in between them. The second I can be substituted for another 2 with commas in between them. So this little production, this recursive production, allows me to get as many I's as I want with commas in between them.
Sean?
Yeah.
How do you distinguish between the empty string and J and the letter E? L? Is that, am I just being picky? Or?
All right. No, you're not being picky, but in my notes I wrote E, so I wanted to be consistent because I didn't bother looking for the lambda symbol. But normally we use lambda for empty string. It's a good question. I didn't want to do one thing in the notes and one thing here. Okay, questions about this? This is a partial grammar because what's missing? Which capital letter didn't get all the details?
B.
Right, I didn't explain what B is, and B is the meat of the language. And B would use a whole bunch of other capital letters to help it. The capital letters are called non-terminal symbols because as you generate them, they eventually will disappear. For example, this now can turn into A, 3, and then empty. That's a terminal string. This is called a sequence of productions, and that's the end of it. You have to have small letters and terminal symbols, and this represents a potential program. Parsing is the question where if I give you a string that looks like this, you have to tell me, is there or can you figure out a way to go from S through these productions to get to the string that I gave you? That's the question of if somebody gives you a context-free language that describes a programming language, and they write a program, you want to look at that program and decide whether you can start from the start symbol of that context-free grammar for the programming language and eventually generate their string representing a program. If the answer is yes, then you've parsed it correctly. And if the answer is no, then there's a syntax error, and your compiler should find out which production it messed up on and give some kind of a guess as to what the error was. And as you all know, sometimes syntax errors aren't so clear, especially when they start propagating way down if you make a mistake early. And there's only so much a compiler can do to guess the mistake you made. All right. Questions so far? Yeah, Gador.
Sample. Would it be possible to learn a sample with Java? I just get lost there.
Oh.
So, I mean, I take everything as you say, but probably with Java will make it a bit more clear.
Yeah, I think with Java will make it a little bit more unclear is what I thought. The syntax for Java is complicated. Even the very first line can be 100 different things. So, I mean, you can do it. It just, even the start symbol, doesn't even have to start. Like in a Pascal program, the program has to start with the word program. What does your Java program have to start with?
Or import.
It could start with import. It can start with the word class. It could start with...
Why don't you write the program Hello World in Pascal on the board? And that way they might understand this a little better.
Yeah.
I mean, write an actual Pascal program up on the board? All right.
Hello World, you know?
Program. I think Joe's got a good suggestion. If I can remember my Pascal syntax on the semicolon. I'm going back to here. Begin, right line, hello, semicolon, end. Actually, there should be a period instead of a semicolon, but I'll make it small. All right, this is a Pascal program that prints the word hello. It starts with the word program. It has a bunch of identifiers here that are often just input-output for the file I/O, a semicolon to end that. This is the body of the program, the thing that we call capital B. And it can start with the word, it usually does start with the word begin. There are some other things that can come before the begin. So the body of a program is actually declarations and then main block. Main block starts with the word begin. In here are the choices of all the constructs in the language, whiles, ifs, and for statements, and then an end to bracket it. So does that help a little more? Maybe not.
Yeah, I guess.
So,
Is Pascal cap sensitive?
Case sensitive? No.
I think
some versions are. Yeah, I think theoretically it isn't, but I guess some versions are. You know what I can do? I can give you not a context-free grammar, but a syntax diagram, which is another way of writing a context-free grammar for Pascal. Maybe that'll help, and that'll give you more than just this teeny fragment. But here's the other thing. You know what? If you don't exactly see the connection to the programming language, you can take my word for it, and that shouldn't affect what we do next. Okay? We're just going to talk about, given a context-free grammar and a string, how can you figure out whether that string came from the context-free grammar? And that problem is independent of the application. But I do have a copy, and I'll Xerox it, and I'll give it to everybody afterwards, of a grammar in Pascal. Is there a syntax diagram in the Java book for Java? Did you know, in an appendix? You know why? There's probably a darn good reason.
There's one for scheme, though.
Scheme is easy, right. The context-free grammar for scheme is easy.
R4. Very nice.
It's in the blue book that we got.
Scheme revision you have.
Oh, it's in the back of that book? In the appendix?
See that spec document?
That blue folder book.
Oh, the blue folder spec document for scheme has the actual context-free syntax diagrams for scheme. So it might be better to do it in scheme, yeah. Okay.
So just before you erase it,
Yes.
The open paren, would that be once it was parsed? Would we get open paren, comma, or semi? How would the words be separated here? Input would be one word that it would read probably, right?
Input would be one of these J's.
Right.
It would be L, L,
Actually, wouldn't
L,
it be
L,
one of
L,
the
J.
size?
Yes.
Which would be made up of.
Which would be made up of the word I. The J part would be the NPUT. The L part would be the I.
Okay.
Yeah, maybe I should do it. Let me go ahead and start to generate this string with this grammar. That may be useful. Let's do that. I want to try to come up with this, at least the beginning of it. At least this part. Let's generate this part from this grammar. We start with S. The first thing is the word program. The next thing is the open paren. So far we're up to here. Now we're in this box that we called an I. Right? So looks like this. What happens next? Now we're going to expand that I out. The I is going to become I comma I. So it looks like this. Program, open paren, I comma I, semicolon, B, end. And now we're going to expand the first I. And that's supposed to be the word input. So we go to here. We say I is a letter followed by J. Program, letter followed by J, I, B, N. The first letter turns into an small I. So program L, small I, followed by,
Would the L still be there?
sorry,
I followed by an
I followed by,
LJ.
I followed by a J. There's a reason humans don't do this. So what happens next is J is going to turn into LJ, and that L is going to be an N. And that J will turn into another LJ, and that L will be a P. And that J will turn into another LJ, and that L will be a U, and then a T. And then J will turn into nothing and disappear.
What
So after
the comma?
the comma stays there.
Came from I, comma I.
Oh, the comma is what made it into the I comma.
So this is what we get after a few steps. Program input, comma, I, semicolon, etc. And then you go through I again. You do the same thing you did before, except this time you generate the single letters OUT, PUT, output. And that finishes that part. Takes a few steps. And then you go to this B and hopefully look through a bunch of other productions that let you start with the word begin, and you get that right line part. So it takes a lot of productions. It takes, I don't know, what, 70, 80 productions to generate this string in your language. Yeah, Kevin?
When we parse the I from the first to the second line there, yeah, you got the I.
How did we know whether to do I, comma, I, or?
As opposed to LJ.
That's why parsing's hard. Kevin's right. How did you know to do I, comma, I? Just because we all saw that we're going to need a comma, and this doesn't give you any comma. And once you go down this road, there's no way to get a comma later. There's a lot of special kinds of context-free grammars which make sure you can cleanly choose between the methods, and that's what parsing's all about. And you can study it for, you can take a whole, 2 or 3 semesters just talking about these techniques. And there's a lot of issues. So excellent question, and
Just wondering
no
if
answer.
There's some way in the notation to sort of say, well, you need to check for this case first, and if we don't find this case, then we can go on down to this.
There's all sorts of
Okay.
There's all sorts of restricted kinds of context-free grammars where you can basically decide, looking at the string, which production you should use. And that's what you'd like to be able to do. The method that we're going to do to use parsing isn't going to have to deal with that much at all. It's going to use a recursive structure, and I'll talk about that right now. I think we're ready. But let me stop still. Questions about understanding this connection? Yeah, Todd?
Does Pascal have reserved words? Could I use if as the name of a variable?
You cannot.
So the tokenizer actually would have to do the check. Is this in, is INPUT a keyword? No, it's a reasonable identifier. Send it.
Absolutely.
So this sort of combines the lexical analysis and the parsing in one step, but really it's a two-step process.
True.
But you might say that.
No. Todd's 100% right. I mean, I said before there's a scanning step, that takes the thing like IF and makes it one token, and takes INPUT and makes it one token. So normally you wouldn't write a context-free grammar to look through an identifier and say INPUT. You would get that as a big group. You would come in as input. It would come in as if. And then in your grammar, you wouldn't have things here that are letters. You would have things here that are bigger groups. And then I couldn't have come up with any piece of a grammar that I thought would be intuitive enough. So I did mix it, and you're 100% right. This mixes it and kind of is a little bit.
But for fairness, the lexical analyzer does just what those bottom 4 rules are. It has to exactly.
There you go. All right. All right. Now let's get to this algorithm.
I'm still really confused by the context-free grammar part. The theory book, which I have a copy of, has a little section on it that uses some English language examples. So
In the theory of computation book, they have context-free languages that have context-free languages for not just for programming languages, but for other things.
for other things.
Sure. In fact, we're going to do that here. That's a good point, Heather. Hold on. I want to get to this algorithm, but maybe here. Here's a context-free language that generates legal parentheses. Okay, legal parentheses. Everybody knows what that is? That means groups of parentheses that are all balanced. That's legal parentheses. That's not legal parentheses. Okay? What are legal parentheses? Legal parentheses are any set of legal parentheses that you can put an open and close around. Okay? So S is any other S with an open and a closed paren around it. Is that the only way to generate legal parentheses? Well, you can also take two sets of legal parentheses and put them next to each other. You can also have nothing be legal parentheses. The empty string is a legal parentheses. So this little grammar generates legal parentheses. Let's generate this one. What's the first production if you wanted to generate this one? You can do SS. The first S is going to end up being this one, and the second one is going to end up being that one. Then you take the first one and you let that be parentheses SS. Then you let the one inside there be parentheses SS again. Then you let that middle one become empty. So this S generates this part, and this S generates that part. All the S's disappear, and you can get this string. Any balanced set of parentheses you can generate with this grammar. Anything this grammar generates is a balanced set of parentheses. So there's a very simple example of a context-free grammar. It's not as fancy as a programming language, but it does generate an interesting set of things, an interesting set of strings. Okay.
Is that grammar an input to the compiler? Is that like written out and then the compiler reads it? Or is it the compiler just built with those rules in mind?
That's a very good question. I'm only hesitating because I knew I was getting myself into hot water here, trying to introduce a subject that needs a whole year just to motivate one example. But nevertheless, it can go both ways. You can write something that takes the description of the grammar as an input and just compiles, and you could also try to fine-tune it to the particular grammar you're working with. So you can go either way. And it's a really good question. They have tools in Unix, right? Lex is a tool in Unix that basically takes a grammar and will parse things according to that grammar.
That's but Lex will do the tokenization.
Oh, I thought Yak did the other one. Oh, Yak does the grammar, Lex does the scanning. Okay. So Yak stands for yet another compiler. So it takes compilers and it takes context-free grammars and parses it according to the grammar. So you write the grammar, it does the parsing. Yeah. All right. You can get a lot of experience writing context-free grammars, and you'll have plenty of time to do it in 3 months. Now let's explain how to do parsing. It turns out that there's one very nice algorithm for parsing that uses dynamic programming. The worst case of this algorithm is order n cubed. It's not too fast. But it does have that same small constant that our example yesterday had. So that's the good stuff. On the other hand, the best parsing algorithms have to run much faster than that. You all know when you write 3,000 lines of code and you compile it, it already takes a few seconds to compile. If it was n cubed, it would take way too long to compile. So generally speaking, your compilers try to run in linear time, time proportional to your program, time proportional to the string that you're trying to parse. That's the goal. And there are compilers that do that. And most modern methods will. So this method I'm going to teach you now is not one that's usually used. But it's one that will give you a nice example of dynamic programming and will introduce you to parsing. This algorithm is usually called the CYK algorithm in honor of the 3 people who, I think 2 of them worked together and one invented it simultaneously someplace else, Cuck Younger and Cassimi. And it's very old. It must be at least 20 or 30 years old, probably a little more than that. It expects the context-free grammar to be in a particular form because it makes the algorithm easier to describe. The particular form that the context-free grammar is in is called Chomsky normal form. This is named after the linguist Chomsky, who's over here at MIT, who did pioneering work in grammars and the description of natural languages. He described the hierarchy of these grammars, and in doing that, you talk about special ways of writing the grammars. A normal form is just a way to say that if you give me any context-free grammar, I can fiddle with it so that it will be essentially the same description, the same language, but the grammar will look a little simpler. I'll clean up a lot of the mess. For example, empty productions tend to give compilers a hard time. You'd rather get rid of them or put them out into one little corner of the grammar. You'd like to make the grammar look as simple as possible. Chomsky normal form is a very easy way of doing that.
What's an empty production?
It's something that goes to a lambda, something that makes something disappear. Having those is a pain. There's other things that are a pain, and Chomsky normal form separates them, compartmentalizes them, and makes it all look very, very simple. Here's what a production looks like in Chomsky normal form. Every single one, for example, looks like this. Goes to either 2 capital letters or to a single terminal letter. If there's an empty production, it has to be in the start symbol. There's no other empty productions. So here's an example of a context-free grammar. Two capital letters or single letters. 0. Lambda. Lambda is only allowed up at the top. Single letter. Single letter. Here I'm using zeros and ones as my terminal symbols, and all the other capital letters are non-terminal symbols. Very simple structure for a grammar. By the way, what makes a context-free grammar context-free? What rules does it have to follow to be called context-free? A very simple rule. A single capital letter on the left side makes something context-free. You can't have something like this. 0s turns into something. That's context-sensitive. That means I can substitute for s in the presence of a 0 on the left side. That's why it's called context-sensitive. Context-free means I can substitute regardless of the context of where you find this capital letter. So it's context-free. Anybody know what this generates?
Binary.
Binary numbers, but what kind? Any special kind? Does it generate all the binary numbers? I'll leave you to think about that, if it's anything interesting or not. And then let's work with an example that we'll try to parse. Here's the grammar we're going to parse today. S goes to A, B, and B, C. A goes to B, A, and 0. B goes to C, C, and 1. C goes to A, B, and 0. We're going to try to parse this grammar. Here's the string we're going to parse it for. 1, 0, 0, 1, 0. Can this string be generated by this grammar? Yes or no? Let's describe an algorithm that will answer that kind of question. Give me any string with zeros and ones. That's are all the terminal symbols. This is a language in binary. And did it come from here or didn't it? Yes or no? All right. Anybody look at this? Anybody got an idea what this is? Is it anything? Just random? Z and O are just substitutes for the letters 0 and 1, right? So this means S can start with a 0 and then followed with an A, whatever that is. Or it can start with a 1 and go back to
Generate gray codes?
generating what?
Gray codes?
They always have to,
Unless I made a mistake, I don't think it does. But
they always have to have
let's look.
even numbers.
Either a 0A or a 1S. If I start with a 0, I move over to A. If I get an A, I can turn it into a 0S or a 1, sorry, or a 0, 0X or a...
O to stand for.
Oh, O is 1, right, or a 1A. Thank you. I chose O to stand for 1. Who did that? Right, I did it myself. All right, so let's look at this grammar. And the S can turn into a lambda, and the A can turn into a 0. This grammar is so simple that we can write it as a finite state machine. In fact, grammars that have just small letters on the left and capital things on the right side of their productions, are actually very special grammars. They're called right linear grammars and the really finite state machines. They're the least powerful kind of context-free grammars you can have. Let's make a finite state machine for this. Here's state S. Here's state A. If I get a 0, I go to A. If I get a 1, I stay here. In A, if I get a 0, I go to S. If I get a 1, I stay here. In S, I can disappear, which means I accept anything that ends up in here. That's an accepting state. And in A, I can go to a 0 and then I accept. So any 0 already goes back to an accepting state. There's a finite state machine. What does it do? I call these A and S. Now I'll give them better names. Let's call this even and call this odd. Every time I see a 0, I go to the odd state. That means I got an odd number of zeros. Every time I see another 0, I go back to the even state. I got an even number of zeros. Every time I see a 1, I don't change how many zeros I have, whether it's odd or even. So the zeros and 1s that end up here are all the ones that have, are all the strings that have an even number of zeros in them. So this grammar generates strings with even numbers of zeros. Now that you know this as a human, if I give you this, you can say, yes, this grammar generates this string. And if I gave you this, you'll say, no, this grammar doesn't generate that string. But we need an algorithm that isn't as clever as we are, that isn't going to stare at the grammar, think about it for a while, say, oh, it's a finite state machine, make a picture, come up with a semantic interpretation, and then say yes or no based on that. We need something completely mechanical that's going to stare at this grammar and figure out, given a string, whether it's accepted or not. OK? Questions about this? So let's go to here. And we don't know what this grammar is doing. We don't know whether this string is generated by it or not. Let's go ahead and run that through. OK, questions? Good. Let's see. This is the part that is the actual algorithm. And we're going to need some boxes, like we always do. We're going to build up the answer to our question of whether this string is accepted by this grammar by filling in this table and by looking here at this box at the end. This box will have the answer. It won't say yes or no, but here's what it'll say. It'll say in this box is going to be a list of all the capital letters in this grammar which have any chance of generating this string. So if S happens to be in here when we're all done, then the answer to our question is yes, S can generate that string. And if S doesn't appear here, then the answer is no, this grammar doesn't generate that string. So in this box is going to be all the capital letters, all the non-terminal symbols that can generate this string. If S is in that list, we say yes. If S is not in that list, we say no. The question is, how does the capital letters that appear in this box relate to the capital letters that appear in all the other boxes? And what do these boxes mean? What is the 1, 5 that represents this box? We need a connection between this box and the other boxes. We need to build this up and figure out what capital letters will appear. All right, so let's call this big table, call it P for parsing. And let's try to figure out what P of ij is going to mean. And again, I always tell you that in dynamic programming, this is the point that you have to be clever, defining what Pij means. And it's not going to be what you think, so I want to, you're thinking, I'm not thinking anything. But
Well, it's not that.
here's what you might think. You might think that Pij, this is P15. The first one will be the top guy, the second one will be the one here. P15, you might think that P15 is supposed to be all the different capital letters that can generate symbols 1 through 5 of this string. Okay? It could be that. And P14, would be all the capital letters that could generate the first 4 symbols. P25 would be all the symbols that might generate the second to the 5th. Well, it doesn't mean that. It's a little bit funnier, because if you did it that way, it'd be very hard to define this recursively. It's done a little bit differently. So let me show you by example. P23, for example. P23 are all the capital letters that can generate a certain part of this string. Which part? The part that starts at the second letter. The 2 means where you're starting. And the 3 means how many letters you're moving after that. So it doesn't mean the symbols, second and third symbols. It means starting at the second symbol, move inclusively 3 symbols down. So P23 is talking about generating the string 001. Did everybody get that example? I'm going to write that out. So Pij is all the non-terminal symbols that generate j characters of our string starting at the ith character. It doesn't mean that can generate the characters I through j. It means that can generate j characters starting at the ith character. Okay. Now we're getting rolling and almost closing in. Questions so far? Let's use this definition now and try to fill in this table. What are the easy ones to fill in? What are these questions? What are these subproblems that you can answer quickly?
The ones that are where j is 1.
The ones where you're generating one character. What capital letters here can generate a single character? Say the character 0. A can generate 0, C can generate 0. How do you figure it out? Well, this is a Chomsky normal form grammar. Everything's either 2 capital letters or a single terminal letter. If you want to figure out whether a single thing can be generated, all you got to do is look through the single letter productions. The capital letters, there's no empties, so they'll never turn into single things. All you got to do is look for the actual single letter productions. Just scan through your grammar once. So let's write this out. 1, 1. That means this first symbol 1. Which things can generate a 1? Just B. 2, 1.
A and C.
That's the 0. Second character, 1 character long. So A and C. 3, 1. It's the same character, A and C. 4, 1 is B, and 5, A and C. That's the base case. We're going to work our way from the top to the bottom of this pyramid. It's a little different than the multiplication where we worked our way down the diagonal. Here we're working our way down from the top to the bottom. We're going to eventually fill in this box. But as we go down, the amount of work we have to do to fill in a box will increase. This was the base case, and it was easy. Let's do the next case. Let's go down to here, 1, 2. 1, 2 corresponds to which substring? Starting at 1, 2 characters down. That substring, the 1, 0 substring. Right? Starting at character 1, 2 characters long. How do you figure out what can generate that? Let's do it in terms of what we already know. We want to generate this string 1, 0. We can generate it in two parts, a left part and a right part. The left part can be 1, the right part can be 0. It's only 2 symbols long. What can generate the left part? A B. And what can generate the right part? A or C. You got B on the left, you got A or C on the right. So how do you generate 1, 0? You look for combinations of these, either BA or BC. Now look at the productions. Are there any BAs or BCs?
Yeah.
Here's a BA, here's a BC. So that means S can generate BC, A can generate BA. That means both S and A can generate the 1, 0. And nothing else can. Because it's Chomsky normal form, you only have to compare pairs. That's why it's so helpful to have this in Chomsky normal form. Doug, do you have a question?
No, I was just kind of thinking aloud.
Be my guest. Think aloud. That's SA. Let's do the next one. You guys should do the next one, because we spend a lot of time introing, and you get tired, and if you want to really get it, you got to do it. So we'll go around. I'll help you if you get stuck. We're going to go to the, yeah.
We didn't have the list of all the different ways of doing it.
We're going to go through everything. Yeah.
Bottom.
At the bottom, we're going to come together with a list of capital letters that can generate all the symbols that are 5 long that start at the first character. Namely, all the capital letters that generate this.
All the different ways of doing it.
Well, unless we remember things along the way, we won't know all the different ways of doing it. We're just going to remember that there is a way to do it. We could store things along the way and remember, like, well, here there's no choice. We had one do the left, one do the right. But as we go on to longer strings, there's going to be a choice as to where we split it in the middle, just like there was for matrix multiplication. So instead of just left and right, it could be the first symbol and then the rest, the first 2 symbols and then the rest. And then we're going to have to remember where we split it. And if you store that information along the way, then over here you can backtrack through it and actually get the list of productions. But Neil's 100% right that it's very important to know that when we finally get the answer yes or no, it would be useful to actually find the productions that get that string. That's a very important point. And it's one of the, I'm pretty certain it's one of the questions on your homework. So I'm not going to show you how to do that, because I want you to do it in this example. But I showed you on all the others so you can mimic it. And I'll help you if you get stuck. Don't go panic. Oh no. I'll show you how to do it if you get stuck. Let's go over to here. Let's just go around. Who wants, Kevin, you want to be the first happy volunteer? So what substring of this does 2, 2 correspond to?
0, 0.
All right, because it's the second, and it's 2 symbols long.
Right.
Exactly.
And either one of them could have been A or C.
Either one of them could be A or C.
So we're looking for AA, AC, CA, or CC.
And now we look through all this list,
And CC is B.
and none of the others are there.
Right.
So this guy gets a B.
We would never do the double symbol, like AA or AC or CA.
It's just not here.
Well, but it could be a sequence of 2. Take that as a no. Just say no.
Just say no. No, we're trying to figure out whether there is a single capital letter that can directly generate these 2 things, which would then give us our string.
Okay, so if we had the double, then it would be not context-free.
Right. Well, that's one way to look at it, yes. All right, who wants to try the next one, the 3, 2? I got a call on people. Erica.
Okay. A, B, or C, B.
Wait, slow. Jeez Louise. 3, 2.
All right. The 0 and the 1.
Because it's the third one and it's 2 symbols long. And you can split this only one way, left and right. So what do you got?
So the first one can be either A or C,
Okay, AC for the 0.
and B for the 1.
So it's, now you can go on. Now I'm up to you. Go ahead.
Okay, so you can have A, B, or C, B, which gives you S, and that's it.
C.
Oh, sorry, yeah. S and C.
S and C. Because you have AB or CB on the right, there's an AB here and here. So it's S and C. Okay, let's shift over.
So 1 is B, and the only two to consider is 0 A and C.
So we get B combined with A and C, which gives you BA
BA or BC.
or BC, good.
And that boils down to A.
BA,
There's an S too.
BC up here.
Oh, BC up there too. Okay.
So S and
S and A.
good. Excellent. Excellent. Everybody, excellent. All right. Here's the thing. Excellent, but it's conceivable that even though you've got it all so far, you still don't actually see the main idea, because this row is dependent on two things that you can actually do in your head. You look at 1, you remembered it from the time before, and 0 from the time before. But we really want these new boxes to depend on the previous calculations we made. Now, they were there, but we didn't consciously notice them. For example, let's go back to here, because the next line we're going to need to know how to do this. Let's go back to there, to the 1, 2. What boxes did 1, 2 depend on? We can only split it in one place. It depended on 1, 1 and 2, 1. 1, 2 are the first two symbols. The left side of that is the first symbol 1 long. The right side of that is the second symbol 1 long. All we have to do is look these two boxes up. They were here and here. BA, BC was the combination. We look through our list. We see the capital letters that go to BA or BC, and they were S and A. So even though you were doing it in your head, the answers were there for you to look up. This one depended on these two. What did this one depend on? What did 2, 2 depend on? 2, 1 and 3, 1. So each of these depended on the 2 that are above them, directly above, and 1 to the right. Every one of those looks at 2 things above it. Let's do the next one, and then it'll start to all go into place, and we'll be done pretty soon. Yikes! Not from here, I didn't. Thank you, Michael. You get to do the next one, smarty pants. 1, 3. 1, 3 means which string?
You can split it in 2 places.
But which string is it first?
1 OO.
Right. It's the first symbol. It's this string, this substring. We're trying to figure out what capital letters generate that substring. And Michael's right. You split it in 2 possible places this time. What are the names of those substrings according to this IJ notation that I have?
1, 2, and 2, 2.
1, 2, and 2, 2. That means the first 2 symbols and the next 2 symbols. That's 4 symbols long, right?
It would be 1, 2, and 2, 1.
Okay, so let's do that. Let's go slow.
Right, okay.
1, 2 are the first 2 symbols, starting at 1, the next 2 symbols. 2, 1. You mean 2, 1? You mean 3, 1, right?
Yes.
The third symbol, 1 symbol long. This is the first 2 symbols. This is the third symbol. I know that this notation is annoying. I warned you it was going to be annoying. It is annoying, and it's easy to mess up. But it does make this work out. So it's a trade-off. Tough luck. 1, 2, 3, 1. That's one combination. That's where you split the 2 on the left and 1 on the right. So,
Right, and then the other one would be 1, 1, and 2, 2.
excellent. You got 1 symbol on the left here, and then you start at the second symbol, and you go 2 more down. That gives you the second 2 symbols. So this is splitting it after the second. This is splitting it after the first. Either one of those might be a possible way for us to generate this final string. We don't know which way might work. We have to try both. So let's look in this box, see what we get. Let's look in this box and see what we get, and see if we get any combinations. 1, 2 gives us SA. 3, 1 gives us... What? We didn't do 3, 1 yet, huh? Oh, yes, we did. That's lucky. Getting panicky. 1, 2 is SA. 3, 1 is AC. So I got lots of combinations. SA, SC, AA, AC.
No SA, no SC, no AA, but we do have none of them.
None of them. Not one of them. Not one way to generate this string of 3 if we split it after the first 2 and the second one. No way to do it. Let's go down to this possibility. 1, 1, and 2, 2. No BB. So there is no way to generate this string. Not one capital letter in this grammar generates the string 1, 0, 0. You need to understand that that does not mean we can't generate the whole big string, because there might be a way to generate the whole big string by having a capital letter say generate the 0, 0 and having another one generate. Pieces of this can be impossible on their own, even though the whole thing is still possible. In other words, if you generate 1, 0, 0, something's going to have to come after it. You can't just stop there. So this is an empty set. There's nothing there. Let's identify geometrically what it is so we never have to do this horrible thing again. All right? I can show you the code. It's in my notes that shows exactly how to go ahead and come up with these indices and make them work. But geometrically, it's a little easier to see. When we did this 1, 3, we started at 1, 2, and 3, 1. That was our first pair. 1, 2, and 3, 1. Nice. I circled them before. Thank you. 1, 2, 3, 1. And then what was the next one? What was the next pair? 1, 1, and 2, 2. Here's what happens in general. You go up in this column, you go down in this diagonal. And you do them in pairs. And that combination of indices corresponds exactly to splitting these things in the right spot. Go up in this column, down in this diagonal. And then you can stop thinking about these details. Let's do one more with these details and with what I just showed you to make sure that that works and try to get a sense of why, and then we'll fill in the rest of the table. Let's do the next spot over, which is now 2, 3. 2, 3. 2, 3 starts at the second symbol and goes 3 symbols down to 0, 0, 1. Okay? There's 2 places to split this into 2 pieces. One is after the first 0, one is after the second 0. After the first 0, what is that string called? What pair is that? Second, 1 symbol. It's 2, 1. The next 2 symbols are called third, and then 2 more, 3, 2. That's 1 pair. If I go and stop at the second spot, I've got 2, 2, followed by. You can start to see a pattern here once you get toward these lower stages, and geometrically that pattern follows. These indices go down, these indices go up, these indices go up, these indices stay the same. That's why we're staying in one column and going down in that column, and here we're going, let's look at it. 2, 1 is here. 3, 2 is here. You can go upwards in the diagonal, go down in the column. Or equivalently, go up in the column, go down in the diagonal. Go in opposite directions, the column above, diagonal to the right. And that corresponds just to these pairs of numbers. And it'll correspond that way throughout. All right, now that you know that, let's go ahead and do it. What do we get for the first pair here? We get this one with a 1 to the right. Any combos there? AS, CS, CC, AC. CC, and that is a B. Any others from the next one? We're going to move down, and we're going to move upwards that way. BB. Any BBs? No. Have no BBs. So that's it for this guy. We're ready to move here. All right, now I'm going to throw back to you guys, now that you know the geometry and you got the idea. Heather, you want to do this one?
Okay.
Okay. Talk out loud, because nobody can hear you, and I have to say what you're saying.
Okay. Well, we're looking. You want the whole.
You don't like my shirt? What do you mean you don't? Heather's actually solving this problem while I bother her.
Well, first we could look at 3-1 and 4-2.
Excellent. 3-1 and 4-2 are the first two you're supposed to look at, starting from the top here and moving upwards in the diagonal there. You get any combos from those two?
Nope.
Nothing. I'll take your word for it. Now what?
3-2 and 4-1.
3-2.
No, 5-1.
3-2 and 5-1. Good. So down the column, up the right diagonal. Any combinations from SA, SC, C?
Another CC.
And that's it? So this one ends up being a B. And that's all. Perfect. Super. All right. We're almost done to fill it in. This one is going to depend on, go down the column, up the diagonal. BB. Let's do it quick. Nothing. Right? There's no BB combination on the right side of a production. SS, AS, AC, SC. Nothing. Empty B. That's automatically nothing because there's no single capital letters on the right of any Chomsky normal form grammar. So, empty. This guy. Up from the top, over to the right of the diagonal. A, B, C, B.
Yep.
What do we get?
Yes, that's good.
B and C. Then we're going down here, B and S, A. So B, S, B, A.
Okay.
Oh, now I think we got everything. B, A, B, C. Another A, but no added extra ones. So everything except B goes in here. Let's go down to here. Finally, after all this work, we're ready to check whether we can generate this whole string. And it will be determined by whether we can split this in any one of the 1, 2, 3, 4 different places we can split it recursively to do the parsing on every one of the pieces. If we originally had split this into all these possible places and done the recursion, it would have been exponential because you get an amazing number of duplicate calls. But since we did it bottom up, we made sure to call each call just once. And that's what makes this polynomial. Let's do the last one, starting from the bottom column, moving our way up. Time elapsed 1 minute. You get all of them, except B again. Since S is in this square, you answer yes, I can get this string. And I say how? And you say, oh gee, I wished I would have remembered where I split the parsing at every stage along the way. That would have helped me. If I would have remembered where I split this, I'd know what box to go back to next, and that would tell me where I split that, and that would tell me what boxes to go back to next, and they would tell me what boxes to go back to next. And I could actually print out the production. But since we didn't, all we know is that the answer is yes. That second part I said I'm going to leave for you. Let's analyze this quickly. Everything in the top row takes 1 step. Everything on the next row takes 2 steps. Third row takes 3. Fourth row takes 4. And fifth row takes 5. And just like before, we have only one thing on the fifth row. So we get 5 steps for this. 4 times 2, 3 times 3, 2 times 4, 1 times 5. Exactly the exact same summation that we did for matrix multiplication. And that summation ends up being about n cubed over 6. So here's an n cubed algorithm where the constant factor is very small. It doesn't always have to be bigger than 1 or big. It's small, it's teeny, and it runs in still asymptotic time order n cubed. Yeah, Kevin.
With the matrix multiplication, the combination step that we were doing to sort of evaluate lengths of how many steps it took to kind of multiply up to that point was constant. But here we have to actually look up in a list of sort of possible precedents. So do we need to take into account the fact that the possibility that the list is incredibly long, that we have to do a look up?
Great question. So again, I'm kind of quickly saying the complexity here, and Kevin's calling me on the detail of the corresponding lowest level in matrix multiplication is just multiplying 3 numbers, and he buys that that's 1 step. But he doesn't necessarily buy that I can answer the question that we've all been doing in our heads, that if I look at 2 particular squares, say this one and this one, and I'm going to combine them in every possible way, that I can figure out in constant time the capital letters that go to those things. What do you think about that? Say I make a list out of these, and I have SS, SC, AS, AC. And Kevin's implying the worst thing I'll have to do is look through all these productions to look for them. And that's going to be time proportional to what? To how many productions I have here. Now, when I tried to tell you the complexity of this algorithm, I did it completely in terms of the size of the string. And this brings in the fact that it may be order n cubed times the size of the grammar. So let's say I grant you that we're not going to do anything fancy with data structures and lookup, and we're actually going to do something, because maybe we could do a little pre-processing and set up these things in an array, and do an inverse index. Maybe we could do it by a hashing or a lookup or something clever. But let's say we're not going to do it that way. The worst that would end up making this be is order n cubed times, call it m, the number of productions in your grammar. Okay? So now let me convince you that even if you did it this bad way, it isn't so horrible. Because generally speaking, what's longer, do you think? The number of productions in your grammar or the size of a production level program? N should be much longer. Your grammar should be something fixed. Say it's got 300 productions in it. And your program could be 800,000 lines long. So for the most part, in this case, very different than the case in the coin changing example, here the m's are relatively fixed and constant with respect to n. So even if it does take a stage that's proportional to the grammar, if that grammar is fairly efficient and small relative to the strings or the size of the programs that you're doing, we think of that as a constant. That's one answer to your question. The other answer is it probably does matter. You really should do pre-processing. You should really try to make these things be 1 step rather than a search. And it could even be bad if this were a very large grammar. You'd even feel it, especially for small strings. So the right way to do it, I think, is to pre-process this grammar so that you can actually answer that question in 1 step by a lookup, which I think you can do. Because how many different combinations of double letters are there? It's just the square of the number of non-terminals. So you could just make an array with that stuff in it and point back to anything that produces it. And I think that's how you'd really do it. Okay. Questions? Okay. Let's quit.